Okay, let me welcome Dr. Gayatri Mishra, now an assistant professor of IIT Kharagpur.
No, not yet.
Okay, well, you have been appointed.
We'll join.
We'll join, and I have shared her bio and everything, so I'm not going to waste any more time on that. Let me give the forum to Gayatri to get started, and we want to listen to her hyperspectral imaging for food processing work. Okay.
Yeah. Is it visible now?
Yeah.
Okay.
Before you start, I would request everybody to please mute themselves so that we don't have any disturbance in the recording. Okay. Thank you.
A very good evening to all. Myself, Dr. Gayatri Mishra, currently working as technical advisor of Spectral Imaging for Doctor Spectra Pvt Limited. It's a Bangalore-based startup. So I basically provide consultancy services to them. Today, my topic is hyperspectral imaging for non-destructive quality and safety analysis of food. Outline of my presentation is I'll introduce hyperspectral imaging technique and its fundamentals. Then I'll cover the imaging system and its components, followed by the application of hyperspectral imaging in food safety and quality analysis. And finally, I will discuss the challenges and future scope of the technology. So, as the introduction, first we'll discuss why hyperspectral imaging is needed in food industry and from where its existence came. So basically, in nowadays, consumers are inclined towards improved quality foods, and they are demanding safety of the foods. And another term now is being trending is consistency of the product. Based on the quality, safety, and consistency of food products, consumers are choosing the food brands, and they are now well aware about the nutritional compositions, what are the adulterant, if there are any adulterant present in the food or not. So to achieve that, we need automation in the food industry so that it can improve the productivity and also remove the human subjectivity and inconsistency involved in food processing operations. To achieve that goal, hyperspectral imaging will be a helpful tool for food industries because it is non-destructive and offer rapid analysis, accurate analysis, and also reliable. So originally, hyperspectral imaging was developed by CAET in 1985 for Earth observation and remote sensing. Even if nowadays the hyperspectral imaging is commonly used for remote sensing purpose, and recently in food industry it penetrated. First, Robert and his co-workers used hyperspectral imaging in lab for agricultural food analysis. So why hyperspectral imaging? Commonly for inline quality analysis, food industries use digital color imaging. But the limitation of digital color imaging are it is insufficient in case of objects with similar color. For example, if there is a adulterant of similar color is present, that is usual in case of spices. In case of chili or paprika, we found some adulterant that is of similar color. In that case, the digital color imaging is insufficient in detecting. The next problem is it unable to predict the chemical composition because the visible light that is used in digital color imaging cannot penetrate into the food material, and therefore it could not predict the chemical composition. It also inefficient in detecting the invisible defects. For example, the normal imaging, the color imaging, that cannot predict if there is any insect present inside a mango or inside a wheat kernel. Then researchers found spectroscopy technique, which is able to detect chemical composition and can also detect invisible defect inside the food material. But the limitation of spectroscopy is it is unable to predict the exact position and location of the defect, because uh, for spectroscopic analysis we need to do sampling, and it give the average amount of the chemical component that present in the food, but it could not detect which kernel is defected or which food material is exactly contaminated with a certain material. So to overcome these limitations, the hyperspectral imaging is an emerging technology which uh, is helpful in detection of the chemical composition as well as the invisible defects. It is the combination of digital color imaging and spectroscopic technique. Now let's discuss what are the fundamentals of hyperspectral imaging. So when imaging term come into picture, the importance is of light is there because it is the optical property. So basically light is a stream of photon particles and carry a certain amount of energy. As we already know, according to Planck's law, the energy is directly proportional to frequency of light, and that energy E is equal to h nu or hf, as I already showed. Uh, in that case, h is the Planck constant and f is the frequency of light. That light, when passes through a prism or any diffraction grating, it produces various wavelengths of light. For example, if we pass a white light through a glass prism, it decomposes into 7 wavelengths, as we already know, that is Vibgyor, as shown in the figure. Then an important concept comes here when uh, the light interacted with the food sample. What happens is that when an electromagnetic wave, that is light, strikes over the surface of sample, some of the energy get transmitted, some of the energy get reflected, and some of the light get absorbed to the food material. That totally depends upon the object property. So from the figure, we can see that if the material is transparent, all of the light can transmit through the material. And if it is opaque, then the light get reflected, or it may diffuse or diffract. And there are other certain principles are there as shown in the figure. And if the light is of lower wavelength, it doesn't penetrate into the food material. It only exit near the surface of the food material, and based on the wavelength of the light which reflect over the food material, based on that we see the color of that material. And if the light is of higher wavelength, it can penetrate deeper into the food tissue and can alter the differential absorbance of that light, and based on that absorbance value, we usually detect the chemical composition of the food material. So this is basically the fundamental of hyperspectral imaging. When the light penetrates into the food material, it alters the optical property of that material, bond energy of that material, and based on that, we usually detect the chemical property. So another important concept is the molecular vibration. When the light penetrates over the food material, the molecular bonds they get vibrated by absorbing the energy. This is a very fundamental concept that when they absorb light, the electrons get excited and jump into higher energy levels. And when it get excited, there are several molecular vibrations occur. For example, stretching vibration and bending vibration, due to which the bond energy of that molecule changes. But the electron cannot stay at that higher energy level for longer time. So to get back to the ground state, it has to emit some energy. And when it emits the energy, it gets recorded by the photodetector and it forms a spectra. That means this is the differential absorbance of that material with respect to the wavelength of light. When we plot it in a figure, we get the spectra, and that spectra is unique to the molecular composition of the material. So here I would like to introduce some terms which are useful for hyperspectral image processing, that are overtones and combinations. So when the electron stays at ground state, it is zero state. Then when it jumps to a first energy level, then we call it as a fundamental uh, fundamental jump. Then if the electron jumps to second energy level, then we can call it as first overtone. Similarly, according to the energy level, the overtones are defined. And if it combinedly jumps to various energy levels, then we can call it as combinations. So based on these overtones and combination bands, the spectral signature of the material is defined. So after discussing all of the fundamental concept, now I would like to define what hyperspectral imaging is. So basically, hyperspectral imaging is a combination of image and spectra. For example, if we capture a RGB image by a digital color camera, so it consisted of three images, such as the image at red wavelength, green wavelength, and blue wavelength. So basically, it is a combination of three images. But in case of hyperspectral image, at every wavelength, one image is produced, and the combination of those images forms a hypercube. And a particular image consisted of pixels, and at each pixel we can find a spectral data which can give the chemical information of the material. So basically, hyperspectral imaging is a 3D image of coordinate x, y, and lambda, where x is the x pixel dimension, y is the y pixel dimension, and lambda is the wavelength. So basically, we'll find at each wavelength one single image, and at each pixel we'll get a spectra. So there are two types of spectral imaging existed, that are multispectral imaging and hyperspectral imaging. The only difference between them is the number of wave bands used for image acquisition. So from the figure, we can see that in RGB, first the monochrome image, which is a black and white image, it has only one image. And if we go for RGB image, it consisted of three images, that is red, green, and blue. And if we go for multispectral imaging, that it consisted of wavelength varies from 2 to 10, and it's a combination of images of number 2 to 10. And if we go for hyperspectral imaging, the number exceeds greater than like hundreds of images are there at a certain wavelength. An image hyperspectral imaging system look like this, as I showed over the slide. The major components are camera and illumination system, spectrograph, a translational stage over which we can put the sample, and a computer which helps in the processing of the hyperspectral data. So the camera, using the illumination source, it get illuminate the sample that present over the conveyor belt, because line by line it captures the images by the camera, and the spectrograph which record the spectral data, and through the computer the data are processed. I'll not go deep into that because we have to cover the application part. So I'm just defining the major components that present in the hyperspectral imaging system. So the flow chart shows the basic processing steps of hyperspectral images. First, the image acquisition is done using the samples. Then the calibration is done. There are various calibration is to be need to do using the wavelength calibration, spatial calibration, curvature calibration, and reflectance calibration to reduce the noise that involved during the image acquisition. Then we get the calibrated hyperspectral image. So simultaneously, we need to do two things. first we have to process the hyperspectral images, and we also need to do the reference analysis, such as if we want to calculate the protein content of certain material. So we have to capture the image, as well as we need to do the weight chemistry method, Geldal method, to determine the protein content of the food sample. And then the hyperspectral data that we collected from the calibrated hyperspectral imaging, using various methods such as spectral extraction methods are there, textural extraction methods are there, using various machine learning techniques. We used to extract the data from the hyperspectral images, and combining those data with the reference analysis data, we usually do the multivariate analysis. And finally, finally, we develop a calibrated model which will be useful for the determination of chemical property, and based on that, we can classify the food material as the normal material or the defective material, like that. So now I'm coming to the application of hyperspectral imaging in food industries. So we can use hyperspectral imaging in various quality analysis, such as in food grain and nuts. We can determine the variety of the grains, and we can also detect the hidden insect inside the kernel, and also can detect the level of infestation, can detect various chemical composition of even grains, fruits, and vegetables. In case of fruits and vegetables, maturity detection is an important parameter which is useful for food industry. Freshness we can detect using that. Similarly, in case of eggs, meat and meat products, and fish and seafoods, the adulterants detection of freshness and various chemical composition detection can be done using hyperspectral imaging. So I would like to give an example of my PhD work at IIT Kharagpur. Using hyperspectral imaging, I detected the insect infestation in stored wheat. So this is the flow chart of the process that I followed during my PhD. So in this experiment, I took a fresh wheat first, then I did a moisture conditioning up to a certain level, starting from 10 to 16, because these are the storage moisture content of the wheat. Basically 10 to 12 is the storage moisture content, but I did up to higher level, because during storage, if the moisture content increases, then the mold infestation might be there, or the level of infestation will also be high. Therefore, for experimental purpose, I took the moisture conditioning up to 16% weight basis. Then to the conditioned grain, I artificially infested the insects, two varieties of insects that were Cytophilus oryzae and R. dominica. Then I stored that infested wheat at 60% relative humidity and 27 degrees centigrade in an incubator. Then up to certain duration, that is at an interval of 45 days up to 180 days. So in 45 days of storage, I extracted some of the infested sample and took the hyperspectral images, and simultaneously detected the quality parameters, such as that which will be which were the indicators of infestation, that were the number of insects, uric acid content, and protein content. And combining the hyperspectral imaging data and the reference analysis data, I developed a principal component analysis model to classify the fits based on the level of infestation. So these images are the indicators of the level of infestation using hyperspectral imaging. So for the colors which indicate the level of infestation based on the brightness of the pixel and the chemical composition. So basically the orange color, the reddish color, which indicates the freshness, the level of freshness in the grain. And as the orange color reduced day by day, then blue color increases in the samples, and the blue color indicates the higher level of infestation in the grain. Then comes my next application, which I did during my postdoc at University of South Australia, that is detection of aflatoxin contaminated almonds and classification of the almond based on the aflatoxin levels. So aflatoxin is a very serious problem in nut industry, because when the producers export these grains, lots of the almond consignments are getting rejected due to the aflatoxin, which is a mycotoxin present in the nuts. So aflatoxin is the mycotoxin secreted by Aspergillus flavus, which is highly carcinogenic. To detect that, usually the HPLC method is the reference method uh, followed by food industries. And to achieve the aflatoxin concentration in almond, the procedure is, first we need to take 10 kg of sample out of 20 tons of almond. Then we have to grind that 10 kg of sample, and then the extracted liquid using methanol, that extracted liquid is used in the HPLC instrument to detect the aflatoxin content in the that 20 ton of almond. So basically, it is a destructive method, and also the sampling process is error, because aflatoxin distribution is non-uniform inside a aflatoxin grain lot, and if the sampling goes wrong, then the consignment is surely get rejected at the export level. So to eradicate that problem, we developed a hyperspectral imaging method to determine aflatoxin content in almonds non-destructively. So first we took almonds, the fresh almonds, and then we artificially infested those almonds with standard aflatoxins, and using hyperspectral imaging and HPLC method for reference analysis method, we combine those methods to detect the aflatoxin content in almonds. So as our results showed, it was very accurate, and the R-square value was about 0.95, and we can see that using the spectral data, we can see from the figure that the fresh almond have different spectral signature than that of the contaminated almonds. So based on the spectral signature, we classified the images, almond images. That we defined as fresh almond and contaminated almond of different concentrations. Apart from that, I've given some examples of research papers. They used hyperspectral imaging for maturity detection in fruits and vegetables. This is particular research by Sao et al. In 2020, who used hyperspectral imaging for ripeness detection in strawberry. And from the figure, we can see that the ripe strawberry and unripe strawberry has a different spectral signature, and using the principal component analysis method, they classified the ripe strawberries from unripe strawberries, and they classification map of the strawberry images are presented in the slide for reference. Then Zhao et al. In 2019, they detected beef adulteration with spoiled beef by taking spoiled beef and normal beef. And they found that the spectral signature of the normal beef and the spoiled beef were different. And from the figure, we can see that the blue color is getting is decreasing, and the red color is dominating as the rotten beef adulteration is increasing in the figure. So they found that the absorption peak at 520 and 560 nanometers in the visible range, they are helpful for detection of the adulteration in beef using hyperspectral imaging. No, it's not that this technology is only have good sides. Obviously, this technique has some challenges, and let's discuss what are the challenges. Hyperspectral imaging contain a substantial amount of data, uh, which pose computational challenges, and also the processing time will also is also high. That is a major challenge, because in industries we need to do the quality analysis rapidly, because we need to do the quality check of each and every product. Because we are doing non-destructive analysis, we are considering non-destructive analysis method. So we have to be very quick. So this is the challenge. And to achieve stability, consistency, and accuracy as compared to the reference methods which are already available in the food industry, that is also the basic challenges of this technique. As I already mentioned, it takes a long time for image acquisition and analysis, which pose problem for implementation in online systems. It contains a series of successive overlapping bands because it's based on the molecular vibration principle, where in the food material similar kind of molecular bonds are present. Then the major challenge is there in case of this technique. So how to overcome these challenges? So as a future scope, as researchers already solved these challenges, when we are talking about a substantial amount of data, some advanced feature selection methods has already been developed to reduce the dimensionality of the hyperspectral images. And to overcome the collinearity or multi-collinearity, and to improve the accuracy and consistency in the image processing data, diverse libraries need to be developed. We have to consider various cultivars, maturity levels, and the data from various harvesting seasons need to be collected, and have to build a diverse library so that the model that finally we develop will be accurate for prediction of the chemical composition. And when it comes to the time, then without taking all the wavelengths, we just need to select the sensitive wavelengths which are useful for our particular application. There comes the multispectral imaging concept. For example, if I'm detecting aflatoxin content in almond or any kind of nut, then only the wavelengths responsible for aflatoxin detection, we need to consider that only, and have to build a multispectral imaging camera to reduce the processing time, to reduce the capturing time, and that multispectral imaging camera can be directly implemented in line for quality analysis purpose. And finally, to overcome the multicollinearity problem, advanced multivariate analysis techniques are being developed by researchers, as now the AI artificial intelligence application is in peak. So researchers are focusing on development of various chemometric techniques, various machine learning techniques for the hyperspectral imaging system also, to improve the accuracy in detection. So this is all about my presentation. Thank you.
Wonderful, wonderful. Thank you. Thank you very much. Very interesting presentation. And don't remove the slides yet. The major thing that I found is your future scope.
Yeah.
Where the most of the work needs to be done, which is the diverse library that you talked about. Basically, mineral libraries are very rich now for mineral resources.
Yeah.
Water resources has a good library. Soil resources have a good library. Of course, mineral. That's what I'm. So for food engineering, that library needs to be developed. So that's a big one, which I think everybody will agree here. And I'm not going to take time away from others. I just wanted to point that's where the whole crux of the research lies, because once that spectral library is developed, then if we go back,
life will be easy. Yeah,
life will become easy. And if we go back to that meat, the beef thing, can you go back there, please?
Yeah.
Actually, one can see, if we want to make a spectral difference, I can see that 900 and 700 nanometer wavelengths are the two wavelengths that we need to really focus on to find out what big difference we can see in the spectral reflectance curve, right? And you said
Yes.
something 500 nanometer. I don't understand.
Yeah. Like in visible range also, because food industries are now looking for low cost technology, and if we are going for infrared range, then the camera cost is very high. Therefore, if we can get some information at visible range itself, then the cost of the camera may be reduced. So they only focused on that particular information. But yeah, obviously from the spectral trend, 900 nanometer is the key one.
So 500, there is some difference.
Some
But
difference, yeah.
I don't see the difference between 50% and 0% in 500 range. One can detect the 100% for sure.
Yeah, of course.
But 0 and 50 becomes really, really fuzzy. So I don't know if that's something. And for the almond, you didn't give us any spectral curve, did you?
Actually, the patent is pending, so I
Oh,
don't have permission to put any result over here. So I'm
okay.
sorry about that.
No, that's okay. That's okay. Let me open now. Anybody wants to discuss, engage, ask a question. It doesn't have to be with Gayatri. You can talk amongst yourself. This is an engagement time period, so the it's open.
Yeah, Gayatri, this is Biswajit.
Yes, sir.
Yes. So very interesting talk actually, and I, being in this food industry, I was looking at how this will be applicable to the industry. That was more of my interest. And like Devu said, yes, the challenge is in the maturity of the system itself. I mean,
Yeah.
the building the library, building the references. So that, yes, so that is where the major challenge remains. And one important question, or rather observation for Debu, was that in that beef example, it's not, I mean, 50% bad beef is as good as a bad and completely bad beef. Okay. So it's
yeah.
either 0% or 100%. That doesn't matter if it is 50% bad. So that, and I think when it should be it should be either good or bad. It cannot be in between sometimes.
Yeah, no. What I wanted to point out was that there is hardly any difference between 0% and 50%. So, so if the meat is actually 50% bad, and we are doing a reflectance at 500 nanometer, it can also demonstrate that it is not bad at all.
It is good. Yeah. Okay. Yeah.
Okay.
I got it. Yeah.
Yeah. Actually, sir, researchers are now focusing in various development of various machine learning techniques, such as deep learning is an usual method which they are adopting nowadays, where they can separate very minute difference as well. Because here we are saying beef chemical composition, but if we are talking about aflatoxins, they are very minutely present in nuts, such as 20 micrograms or 10 micrograms per kg, which is very minute. In that case, the spectral signature will not be visible that different if it is visible to our human eye, but the machine learning techniques can differentiate those minute difference in the chemical composition.
Yes.
Yeah, that I accepted, and that is where I mean the maturity of this entire system has to come in there.
Yeah.
And yeah, of course, with the computation ability increasing, yeah, I think it will be not very far off that these type of technologies will be applicable made applicable in the industry.
I say a very careful yes to machine learning. Okay, very, very careful yes, because I have been using machine learning for last 20 years, right? It is difficult. It is difficult to even differentiate something of this order, but it's not impossible. Okay, let Arsidas is saying something, right?
Yeah. Hello.
Hello,
Yeah.
sir.
Am I audible? Congratulations, Dr. Gayatri.
Yes, sir.
Congratulations, nice work.
Thank you, sir.
Actually, I find this work is very interesting, and also a lot of future scope is there.
Yeah.
I have a submission that now there is a problem with the fish, that
Yeah.
it is getting contaminated with the microplastic or some intoxicant. So can this study be extended to detect such type of contamination in the fish industry as well?
Yes, sir. Yeah, it's applicable because as fish is a perishable product, it's very easy even to detect because light is uh, more like what you can say the food material with a higher moisture content that can
Yeah.
absorb light more. So
Particularly nowadays, they are concerned that almost all the sea fishes, they are getting contaminated with the microplastic due to
yes,
this letting the plastic, other things in the sea. So this microplastic is creating problem in
yes,
the so many articles have been read in the newspaper, etc.
yeah.
This technique, if can be applied with little changes, other things, that will be great help.
Yes, yes, sir. That's a very good idea. Even with this suggestion, I can write a project proposal and then
Yeah,
submit.
yeah. Nowadays the people are very conscious about the food quality.
Yes,
With
yes,
the rising income in countries like India, people are also more concerned. We find in the all the roadside shops also, these nuts, etc., are being sold,
yes,
which was a dream in 20 years back. So this your topic will be very much demand. And only thing, as you told, it should be affordable to the industry.
yes, of course.
Yeah,
And even the industry should be more organized so that
yeah.
in for street foods, I don't think it can be applicable. And most of the adulteration are present in street foods. So in India, that is also a big problem. I agree.
Anyway, this is a nice work. Congratulations. And
Thank you.
also, we hope that you should get your patent at the list.
Yes.
Thank you,
Okay, thanks.
Dr. Gayatri.
Yes.
Okay, anyone else? I have a lot of questions, but I can always talk to Gayatri some other time.
Hi, Gayatri. That was an excellent presentation.
Thank you, sir.
So I have a couple of questions.
Yeah.
How expensive is this technology actually? And is it widely used in food industry currently? What is the status of this technology actually?
Status, sir, in lab, it is feasible. Yeah, using various machine learning techniques, we are now successful in determining every chemical composition, every adulterants. But when we are talking about applying this technique in practical case, like in inline application, the speed of detection and cost, these two are posing challenges in application. So people are now trying to develop the multispectral imaging system, which only consider the sensitive wavelengths, like few wavelengths, starting from 3 to 10, using those wavelengths, we can develop a low-cost system which can be helpful in quality analysis rapidly as well as cost-effectively. So this is basically the status.
Since you mentioned about aflatoxin, on almond,
Yeah.
so I don't think you can give us the results, right? You said it's.
Yeah.
I was interested, if you had any publications or something.
Yes,
I'm
I have.
working now.
Yes, I
So,
have. Yeah, from my
I'll
Google
be.
Scholar, sir, you can find all the publications.
Yeah, I'll be very happy, if you can share it with
Yeah,
me.
sure,
Right.
sure, sure, sir. I'll mail you.
Yeah, right now I'm working with pecans,
Yeah, I'm
but,
aware of that. Yes, sir.
yeah.
Yeah.
So when are you coming to US again? You remember last time we went to
Yes, yes, sir.
that long bus
Las
tour,
Vegas.
right?
Yes.
Las Vegas. Yes. Yeah.
Yes, sir.
Thank
Yeah.
you so much.
Yeah.
Yeah, please go ahead. Please.
Yeah. Yeah. I was sort of like, if I get opportunity for some conferences, IFT, ASAB, all the time, IIT fund those for those conferences, then yeah, we'll meet soon in that.
Thank you so much.
Yeah, thank you.
So I still have, I'm still stuck with a question here.
Yes.
Visible spectrum. Okay.
Okay.
Visible, we usually go for a spectral reflectance, entire spectrum of reflectance. You have shown up to 1,000 nanometer, which is okay. Thermal near shortwave infrared.
Yeah.
We go for the entire spectrum to be a scavenger, right? We scavenge into where we can see the maximum separation,
Yes.
right?
Yeah.
Now, if people go for visible spectrum in food quality or food moisture content, food maturity, and like Rama asked, for fish and plastic, we can probably detect, okay, more easily, because plastic is a different material than the flesh.
Fish. Yeah.
Flesh. So that can be easily detected. But when we are talking about a toxin toxin material, and you are going for a visible spectrum where
No,
we
no, no,
cannot
no. We just
scavenge it,
can't. Yeah. That will be difficult.
that will be difficult, right?
Yeah.
So
If at all the mycotoxin is fluorescent, then we can go for any visible wavelength. Otherwise, we have to go for an NIR range.
yeah. Okay, good. Now we are on the same page, because your diagram was bothering me.
No, it's for meat only, sir. And this is not my work, actually.
No, I know. It's
Somebody's,
somebody
yeah.
else's work, but
Yeah.
that was bothering me a lot. Anyway,
Yeah, I'll change.
yeah, here is another one where here we can go for a visible range. I
Yes.
can see like 600
Yeah.
nanometer.
For perishable foods, yeah, we can go for a visible range.
550 nanometer, we can actually detect very nicely.
Yes.
Actually, in near infrared, you cannot detect anything here. No. Near infrared, you cannot absolutely.
Yeah, because from starting from 800 to 1,000, the water overtones will be overlapping in that point of time. So and the strawberry has very high moisture content. So yeah.
So shortwave infrared gets absorbed. Yeah, near infrared, shortwave infrared gets absorbed. Okay. No,
I suppose all the food items would have a high moisture content. So maybe what Gayatri is saying, that we use lower end wavelengths could be applicable. Yeah.
Yes, for perishable foods, yeah.
Yes.
And if in case of nuts and grains, those are durable foods. In that case, we have to go for NIR range,
Yeah.
and that will be helpful. Yeah, and even that will be costly, of course. But if we are going for expert purpose, then yeah, it can be applied. Then it will be cost effective.
So what about milk? Rotting milk, and how can we detect that?
Yeah, using visible range.
Yeah.
Detect
Only visible range, right?
Yes.
So the blue light reflectance will be the major one.
Yeah.
Blue green. Okay.
Even for liquid samples, still it's a challenge. I have not mentioned here. I forgot that. Yeah, for liquid foods, it's a posing challenge, because when we just place the liquid material over a conveyor belt, it may spill, or due to the wavy nature of the liquid material, the image may not come good enough for detection. So people are also working for liquid food samples as well, where we can apply it over a conveyor belt.
Yeah, the lower wavelengths will
It might be, yeah.
They will just reflect, or what do we call it?
Reflectance.
Yeah, reflect.
Deflect. Yes. More deflection from there. Okay. Okay. Anybody else?
Gayatri.
Yes.
Gayatri, can we detect also microorganisms in food or not? Like E. coli, salmonella, and all?
Yeah, it can be. Because when microorganisms grow over the food, the chemical composition also change. Then it can be detected.
Actually, the thermal band can detect that. Ajit Babu. The thermal band can also detect, because when the microorganism
Heat must be
grow, they emit more heat. So you can You can use
Yeah.
the thermal band versus a visible band or something like that. I'm thinking. Okay.
Yes.
Now, can we just detect or we can quantify it?
Visible band you
Uh,
can quantify probably.
Actually, directly we cannot quantify. We can set up indirect relationship based on the chemical composition. That way we can do.
So blue green algae in water bodies, we are able to determine their growth, right?
Yeah, blue-green algae are visible, that's why. But if we are talking about E. coli, that are not visible to
E. coli
like food materials. That's why I'd say also a challenge.
correct. E.
Yeah.
coli is, I agree. Yeah.
Gayatri,
Yes, sir.
hello, can you hear me?
Yes,
Yeah.
sir.
So, any food industry is now using this technology for quality analysis now? Any industries adopting this now?
No, sir. The startup company for which I'm currently working, they are they are trying to now develop a system for detection of egg freshness and egg egg spoilage. They are trying to detect,
Yeah.
but I don't think in India
Rama,
nobody.
yeah. Rama sir has asked about the plastic. Actually, in fishery, lot of issues there. Actually, due to the formalin issue, now the quality and freshness, people are using some kit, but still there are a lot of scope to do the quality, in particularly in fish. Actually, so I hope this work will be lead. So there will be a solution definitely, particularly in export. MPDA is exporting crore rupees.
Yes,
So it will be very benefited after, as you say, machine learning, all those things should be included, this quality analysis.
yes,
I hope.
yeah, yeah.
Sudhanshu, there is a big
Yeah.
scope
Thank you.
in food industry. Coming up with this reflectance curves that Gayatri is talking about. One that you are seeing right now. These reflectance curve for every type of fresh food and whatever contaminant you can think of or whatever problem you can think of. Okay, that if once that library has been developed, okay, then
Yes, sir. Yes.
people can scavenge. So what I'm trying to say is, if you really want to get into this business, you can grow your own, develop your own patent, just like Gayatri has said. You can develop your
Yes,
own
sir.
patent by just coming
Yes,
up
yes.
with,
Yes.
all you need is a spectrometer, photospectrometer, okay, in your
Yes.
lab.
Yes, sir. Yes.
Then think of 10,000 things that can be wrong with the food, and develop this spectral reflectance curves for each one of those. Okay. Once you have done that, you are actually providing a very good information to the public. So this is a great area to look into for food in
Yes, sir.
food.
Yes, sir.
Dr. Gayatri, am I audible?
Yes,
Yes,
you
sir.
are.
Hello.
Yes, Dr.
Hello.
Shah. You're audible. Yeah.
Yes, I have one question. What is the maximum limit for that is specified by Codex about this aflatoxin level? Total aflatoxin. What is the maximum limit that is allowable?
Yeah, 20 microgram per kg, sir.
20
For
microgram.
actually, it
And
varies,
what about
depends upon the product. Like for nuts, it is mostly 10 to
nuts?
20 microgram per kg. Like 20 ppm, we can say.
ppm or PVP? PVP, I think.
20,
20
yeah,
microgram per kg
microgram
means
per kg.
that
Yeah,
become 50
PVP.
parts per billion. PVP.
Billion, yeah,
PVP.
yeah, correct, yeah.
And since this Gujarat is a region where mostly these nuts are exported, okay, but till now they are not using this technique actually. Okay, they are using only for like they are using this irradiation technique for any microbial like
Disinfestation.
microbiologically there is a problem in expansion, and they are doing that one. But aflatoxin level they are not doing this one.
Yes.
So
Yeah.
is this technique only detect the aflatoxin or directly measure the aflatoxin level also, or you need
We can measure. We also can
measure
measure we can quantify the aflatoxin level as well.
with the image analysis?
Yes.
About the aflatoxin, in the US, it's about 20 ppb actually
Yes,
in the
20
US.
ppb. Yeah.
Yeah, and at 12% moisture content. And
But
that's
for
true of
European, they are a bit
15.
low, I think, 4 years, 4
15.
micrograms. Now 15 for actually that
15,
depends
yeah.
upon the product, sir.
Mhm.
Mm.
No, in the US, it's for human food as well as pet food. So that's the
Mm.
maximum 20 ppb.
Yeah.
Yeah.
Anybody else? has-
Gayatri,
Yes.
sir, I think we'll all agree that IIT is going to get a great professor.
Thank you so much, sir.
So actually you mentioned about so many challenges with this technology, particularly when you mentioned about the long time for the image acquisition, and there are some other challenges also. So in your opinion, I understand that you have been doing this work for the last 7 or 8 years.
Yes.
Okay. So what is the major challenge that is preventing this from the commercialization?
Yeah, cost, sir.
Cost is the only one.
Cost and yeah, time as well. Time is also a factor
That
because
is what, if the time is the constraint, major constraint, so how can we improve that time
Yeah.
required for the image acquisition? That is very
Uh,
important.
So using two methods. First is the multispectral imaging that I mentioned, using few wavelengths which are particularly sensitive for the material that we want to detect. That one way, and another way is using deep learning methods like CNN or RCNN. These are very emerging deep learning methods which will be used for in like expediting the quantification process or
And can we think
regression
about
process.
something between multispectral and hyperspectral, where the number of images can be kept somewhere between 10 to 100 or so?
Yeah, 10 to 100. Yeah, we can do that. But
Now,
at-
will that be helpful in reducing the time as well as the cost? Will that be helpful?
like
It's called
multispectral imaging is the
mesospectral.
simplest one.
Mhm.
It is called
Intermediate spectral.
Sir?
It is called mesospectral. Mesospectral. That method exists actually in satellite imagery.
Yes, that is what I
Yeah.
asked. So if it is possible, then maybe she can be in a position to reduce the cost as well as the time taken for the
Even without compromising the accuracy.
right.
Yeah.
Sanjay, but the problem I see is if you use a mesospectral method, you don't get this continuity. You will get lines that are that are connected.
Yeah, they're discrete. It will be discrete.
It will be very discrete. The mesospectral method.
We'll miss some information there.
Yeah,
as well.
we can miss some information. Is what.
Mhm.
Yeah, we could miss.
No, if we miss, will that be that important? For example, actually, we'll be taking some samples also. No?
Gayatri, you can answer this one.
Yeah. Even I'm also finding some method to reduce the cost and time because I'm also working for a industry and they are facing a lot of problems, and we are trying to develop the first hyperspectral imaging system in India. Let's see.
Okay.
Yeah, okay. All the best, Gayatri, for that.
Thank you. Thank you.
I will be looking forward to hearing from you again on this.
Yeah.
And Sanjay, I think Sanjay's point is valid in the sense that it is not it's not important that it should the detection has to be very accurate. It has to be more like for either the product is okay to be accepted or rejected.
Right.
So if it is like I don't know. I mean, I'm not an expert in these wavelengths and these graphs and all. But if a discrete data can help us in that is absolutely fine.
Yeah. You got a very good point, sir. Actually, using those discrete method, yeah, we can classify whether it is a
Yeah.
good or bad. We just can't quantify exact concentration, and where it is accepted that we can only classify good or bad, then we can go for that.
Yeah,
This-
that's the first point. And then
Yes,
after that, like for example, like your example of aflatoxin. Yeah, okay. But there it becomes important that you get the accurate measurement of the aflatoxin. Yeah, but generally speaking, in an industry where the large scale of products are moving through on a conveyor, it becomes more important to sort out the quickly and remove the bad ones from the product.
That can be. Yeah, we are also working in that way, sir. Not going for exact concentration, focusing on classification only.
Yeah.
Yeah.
So long time back, Suranjan Panigrahi used to work on this just in the spectral band. He used to detect bad apples from good apples. That's how he started his whole work, research work. And I don't know what method he was using at that time and what kind of sensor it was. But it was very primitive, definitely. And now things have changed, and hopefully with the technology growing over years, we will see more and more accuracy and from the lab to the belt is what we need to really get into, right? Things are improving over time, and I hope some of us, our future students, can go and do stuff, CATians or IITians who can get into this area. Because there is a lot of scope. You can just build your own patent,
They were missed out NITians.
Also NITians. Yeah, Winnie is for the fish. Plastic, we need to be a good person to collaborate with. So that's the purpose of the tea talk, right? I mean, we want to grow this CAET fraternity or whatever you call it. I shouldn't call it fraternity, but we'll see how we can help each other and get to a point where we can get CAET a brand name. That's it. Right?
Yes.
Okay, we have 3 more minutes. We can take one last question or discussion or comment. Prabhat Babu has joined now after a long time. He can, if he wants to ask a question. He doesn't have audio though. I don't know. And we have Rao. Rao hasn't asked a question today.
Sir, I joined very late today. Am I audible?
Yes, you are.
Yes.
Yeah, I had a question, but I didn't go through the entire presentation, so I just waited. But since you said, Gayatri, is there any attempt at using gas sensors along with the hyperspectral imaging? Because to understand food, it is the visual aspects as well as the smell that generally a layman uses.
Correct.
In the context of automation or real-time detection, gas would be very helpful. Is there any attempt at doing that?
No, not yet, sir. And I don't know from where you got this information, but yeah, it's a very interesting topic. And even I already wrote a proposal to combine electronic nose and electronic eye so that we can find the overall quality of the food material. So yeah, no, it's not yet right.
Yeah, I did get this information anywhere. It's just a general common sense. When you look at a food, you smell it and you see it. And since I work sometimes in automation, I think that would add to the accuracy of the detection. I mean, you are leaving half of the part of detection. You're only concentrating on this blast.
Correct, sir. Actually, we are still struggling with this imaging technique and development of various machine learning techniques. So it another challenge by combining the sensor part also. So researchers are now going one by one. So that's why I think nobody has tried yet.
Gayatri.
Yeah.
Yeah, you mentioned about sensors. Suranjan is my co-PI in that the big grant with Ghana. So he's going to develop sensors to detect aflatoxin on sorghum. And once it is developed, we are going to take those sensors to Ghana and give them to farmers and collect data. And yes, that he's going to develop a sensor to detect aflatoxin on sorghum. Yeah.
Okay. Okay.
Well, it's 8:30 on the dot in India. So I want to thank Gayatri. Today was a great show, 22, 23 at peak. So that's not bad at all. And thank you, Gayatri. We wish you all the best in your future endeavor as the faculty member. And hopefully you can train more and more CAETians.
Thank you so much. Thank you. And thank you all for giving me this opportunity to present in front of you. So yeah, thank you so much.
Thank you.
Thank
Nice
you.
presentation.
Thank you.
Okay.
Goodbye. Congratulations, Gayatri.
Thank you.